Okay, so we'll start to do some problems to practice on these modes of heat transfer. In the first problem, a glass window of width 1 meter and height 2 meters is 5 millimeters thick and has a thermal conductivity of Kg equals to 1.4 watt per meter Kelvin. If the inner and outer surface temperatures of the glass are 15 and minus 20 degrees respectively on a cold winter day, what is the rate of heat loss through the glass? So as we mentioned already, when we talk about rate of heat, okay, we should provide the value in watt. However, if they talk about heat flux, you can provide the value in watt per meter square. So as a first step, this problem will help us into knowing how we design windows. Okay, you know that for a building, the majority of losses, one of the big part of losses between indoor and outdoor spaces, in case we are in winter, heat will go from inside to outside. And in case we are in summer, we'll have heat from outer space to inner space. And in both cases, we don't desire in general this, because during winter, we want to keep a high temperature inside. And during summer, we don't have to have, we don't want to have overheating inside. This is why we should carefully design the glazing, okay? And as you can see here, if we consider single glazing in general is not a good approach, because it will be characterized by a high value, if you want, of heat conduction from inner to outer space. So, and this will lead to higher heating and cooling ventilation loads. Okay, so first we want to calculate what will be the rate of heat loss through the glass in case we have single glazing window. In case we have single glazing, we just have one layer. Okay, so mainly we have that conduction will take place through this layer. And what is the formula of the conductive flux? Which formula should I use here to determine the conductive flux?
Ka delta T.
Yeah, the flux is minus K dt by dx. The rate is minus K dt by dx. So since I want a rate here, it's minus K times area times dt by dx. Okay, so the result will be in watt when you do this. First, as we already mentioned before, whenever K can be given in watt per meter Kelvin or in watt per meter degrees, it doesn't matter, because delta T in Kelvin is equal to delta T in degrees. And the minus sign is used because of temperature, due to gradient of temperature, heat flux will always go from higher to lower temperature. This is why, if you consider this is the positive x direction, for the flux to be in positive direction, then you should have the temperature at this level larger than the temperature at this level. This is why you have the negative sign here. So here it's a simple application for the first case. So you just have to do minus 1.4 times the area. The area of your window is given because you have the height and the width. So it's 1 times 2. So for the area, we just replace by 1 times 2. Now, we can assume linear profile of variation of temperature within the window. Because you can assume linear profile, you can deal with dt by dx as follow. You can just say it's delta t over delta x. And since we are considering the x direction like this, so it's from outside to inside, okay, then we should do T2 minus T1 over delta x. This gradient will be negative because the outer temperature here is larger than the inner temperature. So T2 minus T1 over delta x. So we just substitute now T2 and T1 by their values. You have that T1 is 15 degrees, T2 is minus 20 degrees, and then you can obtain the value of the conductive flux. So we get the following. We get that when we use single glazing, okay, in absolute value, the value of the heat flux is 19,000 times 600 watt, which is very large. And here it will take place in this direction. So it will go, of course, from the highest temperature to the lowest one, okay? So if we consider, for example, this is the inner space, and this is the outer space. During which is here characterizing a winter season, you have a lot of heat loss through the single glazing. To reduce this heat loss, we can design double glazed windows. In case of double glazing, what we do is we add, in addition to the material here and here, we add an air layer. And this is also described in the course material. But in the course material, you will see that this air layer thickness should be optimized, because if you have a relatively small thickness, the dominant mode of heat transfer through the air layer will be by conduction. And this is good because air is a good insulator. The conduction is small. However, if you increase a lot the thickness to a certain extent, if you increase it a lot, it's true that larger the thickness, you will have smaller rate of conduction, but also if you increase a lot the thickness, you will have like a big gap. And in this big gap, you can have fluid motion. And this fluid motion will lead to heat transfer by convection within this air gap, which is bad. Because what you want to do is you want to increase the resistance to heat transfer. So this is why we say that to enhance the insulation properties of the envelope, we should optimize the thickness in a way to reduce the conduction much more than we increase the convection. Because if we increase a lot the thickness, we can now have a negative effect, since it's true that heat transfer by conduction will decrease, but on the other hand, heat transfer by convection will increase. And then we can have, if you want, a dominant effect for convection, which is not desired. So here, for example, we tell us that if we put, let's say, in a thickness of 10 millimeter of air, we want to see what is the conductive flux through air. We can calculate it if we know the temperature at the inner side here, and at the inner side of this port, okay, and of the outer side of this port, okay. So you can see here that if they gave us T1 and T2, we can calculate this flux. We can just do the same methodology. We apply minus k dt by dx, and this will be equal to the conductivity of air, which is much smaller than the conductivity of single glazing. From here, we can expect that the flux that will go through air is much smaller. And you have delta T over L. So here, the temperature difference, as you can see, here it's directly given for you, but actually in calculations, I will not give you 10 and minus 15. I will tell you why. Because in general, they just give you the outer temperature, which is 15 degrees, and the inner temperature, which is, here we mean by this temperature is the indoor environment. So I will call it inner. So they will give you the inner temperature, which is 15, and the outer temperature here at this level, which is minus 20 degrees. Okay, and you can find by calculation what will be the temperature here at the limiting the air layer. How to do this? I will introduce the idea here because it's an important idea. You can treat this system as an electrical circuit analogy. So you consider that heat is transferred first through this small layer, okay? Then it's transferred through air. Then it's transferred through the second material, okay, here. Who can tell me if I want to get the detailed temperature variation and I want to find what is the temperature at this level, and what is the temperature at this level. What is the equation that will drive this problem? Do you have an idea? What can we say about these fluxes through the system? Yes, Q is the same. Because the Q is the same, I can write the following. I can write first Q K of this layer, okay? So this is kg if you want, times the area, times, I will directly take the absolute value, okay? So I will take the inner temperature here, which is 15. So let's say this was 15 degrees. I know it, it's 15. Minus T at this level. I don't know the value of T here. I will call it TR1, okay? And so I do 15 minus TR1 over the thickness of the first layer. So over, let's say, if I have here a distance of 5 millimeter, for example, so I use 5 times 10 minus 3 equals to, for the air layer, it's K air times the area times T R1 minus T R2 over the thickness. So let's say it's here 10 millimeter. So 10 times 10 minus 3 equals to K, the second, if you want here, you have a second thickness of glazing. So K glazing times TA2 minus T outside. T outside here is minus 20. So minus 20, it's plus 20 over 5 times 10 minus 3. Okay, so you can use this equation. You have a mathematical property that is telling you that if you have A over B equals to C over D, you can do the summation. You can do A plus C over B plus D is equal to each of these terms. Okay, this is why a good idea here will be, after simplifying the area, so you can simplify first the area. Okay, after simplifying the area, you can take K term to the lower side, and here you do over Kg, here you do over Kr, and here it's over Kg again. Okay, now when you add these terms, if you add the numerator of the 3 terms and the denominators of the 3 terms, you will have this 15 minus TA1 plus TA1 minus TA2 plus TA2 minus 20. What will happen is that you will have these terms will cancel out because you have minus TA1 plus TA1 minus TA2 plus TA2. Okay, so in total you'll get 15 plus 20 over this whole term, and you add all denominators together. So 5, 10 minus 3 over Kg, and because you have it 2 times, so I will put it times 2. Okay, plus 10 minus 3 over Kf. So now what will happen is that you know that this factor is equal to A over B and is equal to C over D. Now you can take this equality with this term, you can get what is the value of TA1. When you equate it with this term, you will get the value of TA2. So this will allow you, by just doing the analysis of steady conduction flux, to determine these temperatures. Here they directly gave you these temperatures because all they want you to see is how the air layer will reduce a lot the heat transfer. If you just apply to air layer to get the conductive flux, you will get 120 watt, which is much smaller compared to this one. So you can see how adding a layer of insulation, of air insulation, can largely reduce the conductive flux. But keep in mind that increasing a lot L can have a negative effect, because it's true that if you increase L, the conduction flux will be reduced, but you will have then currents of convection. So you should not increase L in a way to have convection dominant over conduction. Okay.
Sorry, doctor, I have a question.
Yes, sure.
In the gas gap, in the gas,
yes,
it shouldn't be there's convection also?
In the gas, there is convection. It's right. But look, whenever you have to have convection, you need current, you need fluid motion. Okay? You mean between glass and inner and outer space? Or
no,
you mean
inside.
Inside. Okay, inside. Look, when you do a very small gap, a very small gap will restrain fluid motion. And if you put air in a very narrow gap, it will not have the freedom to move. And because you have small velocities, or relatively velocities very close to zero, convection is nearly zero. Convection will be enhanced if you have fluid motion. And fluid motion will start when you have a relatively big thickness, because when you have a big thickness, this will give possibility of currents of air, and this will lead to convective fluxes.
How do we know the range of the thickness?
Exactly, it's experimental. You cannot know. You need to do experiments. In general, they do experiments, and with experiments, you can see how the convective coefficient H is altered by the thickness. So when they do experiments, they do the following: they draw like a curve, H function of L. Okay, they see how H is varying with this thickness, and then they can plot like a graph how convection is varying with L. So let's say for very small L, convection is very small, close to zero. As L will increase, convection will increase. On the other hand, if you draw the conduction profile, it will be exactly the opposite. For very small for very small values of L, you have high conduction rate, and as L increase, conduction will decrease. Now, when you do summation of these two, when you sum conduction and convection, because you know that in at the end you will have both processes. Yani you want both to be to not be at a very large level. You can optimize if you want the total heat transfer. When you draw the total heat transfer, you will get like an optimal length for which this heat transfer is minimized. Okay, so you will work with this optimal length. Okay,
thank you, doctor.
Welcome. Any other question? So let us continue with another problem. A heat flux that is applied to one face on a plane wall is given by Q second is 20 watt per meter square. The opposite face is exposed to air at temperature of 30 degrees with a convection heat transfer coefficient of 20 watt per meter square Kelvin. The surface temperature of the wall exposed to air is measured and found to be 50 degrees. Do steady state conditions exist? If not, if the temperature of the wall is the temperature increasing or decreasing with time? Do you know what is the condition in general for steady state case? How we can ensure steady state conditions? Look, in heat, if you think about heat, you have a certain, let's say wall, okay? You have a wall. to ensure constant temperature and steady state conditions, what should we have, do you think? Yalla, who can tell me, if you just think logically, if you have a body and you don't want to have increase or decrease in temperature, what should be the net heat flux with the net heat exchange with the environment? So if you have a flux that's coming in, you should have exactly the same flux that will get out. In case you assume, of course, no generation. And here you don't have an internal source here inside the wall. You're not burning a fire inside the wall, or you don't have a chemical reaction inside the wall. So if you just consider that what is getting inside will go outside, then there will not be variation in the temperature of the wall. Okay, now if we read this problem, we have different conditions from two sides. Okay, we have at one face we are imposing a flux of 20 watt per meter square, and we have the area is given. We can calculate the area of the if you want of this wall, but you will see that we don't need the area. You know why? Because the area of the inlet here of this face is equal to the area of the other face. So the area will cancel out when we do the analysis, because we can say that Qn is equal to 20 times the exposed area, while for Q out we are losing heat from the other side by which type of heat transfer? We have convective heat transfer, and they gave us what is the convective coefficient. The convective coefficient is H equal to 20 watt per meter square Kelvin. So what will be the
لا ابدا ما بأثر. هي صوتها توشطك ولا مش عم تسمعها؟ اوكي.
Can you please mute the microphone?
ما مركزة معها ابدا. خلصت.
Guys, can you please mute the microphone?
يعطيك العافية.
Okay. So you have here the convective coefficient is
okay.
20.
مثل الانجينير يعني.
Yeah, please. Can you mute the microphone, please, when you talk?
بيتفاعلوا معك؟
Do you hear me? Please, في حدا حاطط الميكروفون on. Can you mute it, please, so that we can continue? Okay. So we have a heat flux through one side of 20 watt per meter square, and from the other side we have convective heat. Since we are imposing here a temperature outside of 30 degrees, we have a temperature outside of 30 degrees, while the surface here is at 50 degrees. Because of this gradient of temperature, you will have loss of heat from the surface towards the outdoor environment. Since 50 is larger than 30, your wall will lose heat towards the environment. And this heat loss can be calculated as a convective loss. It's equal to H times A times delta T. Now, the convective coefficient is given. It's equal to 20. So we just have to replace. The area is not given, but it doesn't matter, as I told you, because the area here is equal to the area at this level. And you multiply by delta T, which is 30 minus 20. Okay? So now, in total, what do you have? You have that the convection flux is getting out, while the heat flux here is coming in. If you compare Qn and Q out, you will have the following. Q out is H times Q second, yani per unit area, is H delta T, you get 400. While Q second N is 20. So you are having a flux getting out much larger than the flux that is coming in. This means if you want to calculate the net flux per unit area, so the net flux per unit area here, is 20 minus 400 is minus 380. Because you are getting a negative results, this means what? What do you expect for the temperature of your wall? It will be stable, or it will be increasing, or it will be decreasing? Yalla, who can tell me what will happen in this case? Look, it's very simple. You have a system, you're having heat getting in, but much more heat getting out. So you are just having 20 in and 400 out. So you are having an outer flux Q out that is much more higher than Q in. This means that in overall, you will lose energy. Okay, so the temperature of your wall will be decreased with time. And you cannot say here that we have steady state conditions, because to have steady state conditions, Qn should be equal to Q out. Okay. Yes, exactly, Yara, it's decreasing. Okay, guys, look, if you don't remember these rules, I can, I will, in next chapter, I will detail them again, how we do the energy balance. But here in this chapter, you can just rely on logic to solve them. It doesn't, you don't have to know all formulas to solve, because you can just do a small sketch. You look what is coming in, what is getting out. If you have more energy loss than energy gained, so of course the temperature will decrease and you will not be in steady state conditions. Any question on this problem? Here, no need to know the area to know if the temperature is increasing or decreasing. But if you want to assess the variation of temperature with time, then you need exactly to know what is your area, because then you need to write an energy balance, and in the energy balance you will need to have the area, but also we'll see together that the area, when it will be present in all terms, it can cancel out, and you will simplify it from the expression. In next chapter, we'll deal a lot with energy balances and how we can calculate temperature variation within a domain. Let us move now to another problem. An electric resistance heater is embedded in a long cylinder of diameter 30 millimeters. When water with a temperature of 25 degrees and velocity of 1 meter per second flows crosswise over the cylinder, the power per unit length required to maintain the surface at a uniform temperature of 90 degrees is 28 kilowatt per meter. Now, when air also at a temperature of 25 degrees, but now with a velocity of 10 meters per second is flowing over the system, the power per unit length required to maintain the same surface temperature is 400 watt per meter. The question is to calculate and compare the convection coefficients for the flows of water and air. In this problem, we are comparing, if you want, cooling effect of two fluids, water and air. Okay. Now we know that convection will depend on several things. First, it will depend on the fluid you are using, because depending on the fluid, the convective coefficient will change, and also the velocity of the fluid. H will be affected by several factors. The fluid you are using in convection, its velocity, and the surface geometry of the body. So here, for both cases, we are taking the same body. For both cases, we have a cylindrical shape. So we are not affecting, we are not playing with the geometry of the body. We are not playing with the size. So you have the same diameter in both applications. And also you are fixing the outer temperature of the cylinder. For both, you have an outer temperature of 90 degrees. You're only playing with the type of the fluid. You are comparing water and air, and you are playing also with velocities. So this will affect the convective coefficient H. To know which mode will be better, هلا أكيد if you increase the speed you expect to have enhancement, but don't forget it's not the same fluid. If it was water here also, so if for both cases you have water, you can be sure that the best scenario will be with the highest velocity here. However, when you compare two different fluids, we'll see that water is much more efficient than air. So even if you have smaller velocity for water, you might have better performance. For this, we need to do calculation, okay? They told us that in the first scenario, okay, we need the power needed to maintain a constant surface temperature is 20 kilowatt per meter. However, in the second scenario, where we have air, we need another flux. We need a flux of 400 watt per meter. So we can now compare, because of this information, we can compare the convective coefficient. And we can expect that because here we need a much higher flux to be used, we can expect that the convective coefficient of air will be much different than the convective coefficient of water. Now, how to do the calculation? All we have to say is that if we want to maintain a constant temperature at this level, okay, we need to give heat. We need to provide heat, because as water will go over the cylinder, you will have loss of heat from the cylinder through water. Okay, and it was found that this heat loss is calculated to be 28 kilowatt per meter, and this heat will be propagated towards air through water first here, and here through air by convection, because your cylinder will lose the generated heat here. It will lose it to water or air by convective effect. To maintain a certain constant temperature here, you need steady state conditions. So the generated flux should be equal to the heat by
Professor, I don't know if you can hear me, but we can't hear you at all.